Hey, hi, good evening, everyone. So, welcome to the live coding.
Good evening, sir.
Yeah, good evening, Lisa. Okay, so we have today week 9 problem solving session, and I hope you have started watching the lecture. And so in the lecture also, professor have discussed some problem with the help of DP. So I hope some DP concept is clear for you. Otherwise, we will discuss the approach using the DP to solve today problems. So we have total 4 problems today, okay, based on the DP, and we will try to discuss all. Otherwise, last 2 problem solution approach is very similar. So what we will do, we will solve first 3, and I'll discuss the approach for the last problem. Then you can try that problem, okay? So because this DP concept is a totally new concept and some practice is required to understand well this. So maybe some set of problems you need to solve to understand the proper concept. Okay, so let me share my screen. Before that, any query, anyone?
No, sir.
Okay. Okay, sir, which topic is important for OPP? Okay, so this is very difficult question because 4 questions will come in the OPP exam. And so important part, I can say, generally I just mention some important area where you can just focus more. So like linked list operations, you can focus. And another part, graph algorithms, at least one spanning tree algorithm, one shortest path algorithm, or PFS or topological sort. These 4 algorithms, like 4 algorithms you should know in the graph unit, week 4 and week 5. And so this is the one, yeah, binary search based problem. Okay. So some binary search concept based problem. And from last week, actually, this dynamic programming. Okay. So, and greedy algorithm also. So generally we not ask very like big code like big 7, this AVL tree, all these things type of problems. But still you should have practice for all concepts till week 9. Okay.
Okay,
Week
sir.
9 is the syllabus. Okay, so we will also release some mock questions. You will get some idea of that. Otherwise, many of the questions actually we have included in our live coding sessions. So do not miss this live coding sessions problem. Also, this time we have this 3 bonus marks for this live coding problems. Okay, and the deadline for this is 14th December. So just complete all the problems, live coding problems to achieve get this bonus marks for the live coding.
Okay, sir. Sir, when is the OPP?
So OPP, there are 2 dates. I think there are 3 slots actually on the 2 dates. So first is on 8 December, another is 15 December, I think. Otherwise, you can check in the grading document. So these are the 2 dates. So 2 slots will be done on the 8th December, and I think 1 slot will be done on the 15th. So
Okay, sir.
okay, so that is happening because of some management of the like combination of the different OPP. So many student takes some combination with the 2 course, 3 course. When all course have some OPP like, so to maintain all the this so like this management, so they are just providing these 3 slots, but they will allocate the students. Okay.
Okay, sir.
Okay. So which we topic important week weeks. I'm not asking what you are asking regarding the week. Lisa?
Uh, sir, that was clear. I
Okay,
was.
okay, okay, fine. Okay, okay, fine. So, okay, fine. So the first, yeah, I have already released the problems for today. Okay. Total 4 problems we have in the week 9 live coding. And we will start discussion from the this live coding problem number 1. Okay. So I hope you have some idea of the DP approach. So DP approach, if we can achieve the overall optimal solution by using the optimal solution of the sub problems for that problem. Then this property, if problem fulfilled, like this is called as a overlap subproblem property. So so in this way we can use the DP approach. Okay, we can smartly solve the problems for the subproblems, and we can use the subproblem solution to achieve the final optimal solution without calculating again. Some basic example is already discussed in the lecture regarding this factorial, all these things, or Fibonacci series. Okay, so this is first problem. You can also try your approach. What approach you can think for this? You can also discuss. Okay, during the discussion. Okay, so I'm explaining. I'm reading the problem statement first. So there are n stones numbered from 0 to n minus 1 for each, where I is greater than equal to 0 to n minus 1. Okay, this is just a labeling of height of a stone. I is hi. Okay, so this is the information given. We have n stone and the height for the each stone is given. There is a frog who is initially on stone 0. He will repeat the following action some number of times to reach last stone. If the frog is currently on stone I, can jump to stone I plus 1 or stone I plus 2. Okay. Here, a cost of absolute value of hi minus hj is incurred where j is the stone to land on. Find the minimum possible total cost to reach at the last stone. Okay, so this one constraint is given. That means frog can only be jumped from I to I plus 1 or I to I plus 2. Okay, so this is the step which is given for us, and if he is actually he's jumping, so there is a cost actually he's losing. So here our goal is to find out the minimum possible total cost to reach at the last stone from the first stone. So this thing, so this type of DP problems mostly are based on some optimality. So where the question asks like maximum, minimum, this type of information. So here also we are just looking for the minimum cost. Write a function. Yes.
So is there any relation, the content, the weak content and these live coding problems, or we can join without going through the content?
No, yes. So this coding problems are totally depends on the weak content. So week 9.
Only OPP? Okay.
No. These problems are based on the week 9 concept.
Okay.
Okay. So what we have learned in the week 9 that lectures. So that dynamic programming concept is covered, and many problems are also covered in the lectures itself. And same on based on that DP concept, we are discussing the problem here.
Okay, so thanks.
Okay, so write a function min cost h, where h is the list of heights for n stones. The function returns the minimum possible total cost to reach the last stone. Sample input is given here h. This h list is given, which represent the heights, and total cost solution answer is given. Okay, how we are achieving this solution, then we will discuss it. Okay, so let me explain this. So what was the 10, 30, 40, 20? So let's. Okay. So I have written the I. So I is representing the stone value. Okay, so stone index or labeling, we can say anything. And h is representing the height of the stone. Okay, so like one stone is there for 10 height. After that, next stone is like 30 height, and next stone is like 40 height, and next stone is like 20 height. Okay, so like this is 10, 30, 40, and 20. Okay, so here the goal is to, so this is the 0th stone, and this is the n minus 1, so third stone. Okay, third index stone. Your goal is to reach from this first point, okay, from this stone to this is the final target. This is the source, and this is the target to reach. And here when we are jumping, okay, so when we are jumping from one stone to another stone, So the cost is, suppose if I'm jumping from 0 to 1. So what is the cost actually? So that is absolute value of 10 minus 30. So that is 20 cost. Okay. From 0 to 1. If I'm jumping from 0 to 2, so that this is from 0 to 1. And if I'm jumping from 0 to 2, so cost will be 10 minus 40, and this is the 30 cost. Okay. So this is the way, and frog can only be jump from I to I plus 1 and I to I plus 2. There are two possibility to jump. So 0 to 1, it can be jump, and otherwise 0 to 2. If frog is at stone 1, so 1 to 2, he can jump, and otherwise 1 to 3 can jump. So in this way, we can follow this rule. And then we need to finalize that what are the minimized cost for this to reach at the final stone. Okay, so here solution is given 30 total. Okay, so suppose if I am jumping one by one, okay, so every in one step at the like 0 to 1, 1 to 2, then 2 to 3. So what is the, this is the one possibility. Okay, this is the one possibility. I am just moving like this, so 0 to 1, then 1 to 2, then 2 to 3. Okay, one step. So in this way, how much cost I am getting that? So 10 and 30. So this is the cost 20. Yeah. And third, this one stone to second index stone, so 30 to 40, 10. Okay. And 40 to 20, this is I am getting 20 difference. Okay, so 20. The total cost I am getting 50. So this is the one possible way to reach from 0 to 3. Another possible, suppose if I am just writing like 0 to 1 and 1 to direct 3. I can do this because we have this constraint. I can do also on I to I plus 2. Okay. So in this way, 0 to 1 is 20, and then 1 to 3, 30 and 20. So difference is only 10. So I am getting 30. Okay. Same way what I can do, I can 0 to 2 and 2 to 3 like this. Okay. This is the one another possibility. So 0 to 2, if I'm just moving, so 10 and 40, the difference is 30, and 10 and 20, 40 and 20 difference is 20. Again, I'm getting this 50. So all these possibility which I can move from 0 to last stone, then we will get a different type of cost. So among all these costs, what is the minimum cost we can achieve? So here you can see these are the possibility we have. So either we can move one by one like this, and otherwise I can move like this, second way, third way, or if there any another way possible, you can also try that manually for the small sample input. Then you can figure out that what solution we are getting, 30. If I choose this way, then I'm getting 30 cost, which is the minimum, and given as a sample output answer. So what approach we should follow here? So first thing, this problem cannot be solved without checking the all possibility. Okay, we cannot directly pick any solution like this. We have to check all the possibility. But how we can smartly check? Okay, without repetition of the same thing. So this type of problem, when you need to check all the possibility, all the combination to achieve the answer, then you can think about the DP approach. Also, that optimal substructure, this property should also be fulfilled. So here we will start from, anyone want to discuss some approach for this?
Okay, we can try Dijkstra's algorithm.
Dijkstra algorithm, how you are applying? So you are making any graph for this?
Yes, so first you have to convert it into edges, weighted graph.
Weighted graph you are converting. Okay, so 0 you are converting, and then 0 to 1, and then 0 to 2 like this. Okay, and 1 to 2, and no, 1 to 2. So you will convert this information into the graph. So I think that is the additional cost you have to do. So how much, any approach you have to convert this?
No, so from the weighted list you have to convert it.
But you have to convert that information to the graph. So I think a costly approach. How much time it will take? You can tell me if you have any specific approach for this. Converting the given information as a graph. Then what you are just trying to figure out the solution with the help of Dirichlet algorithm, correct? Okay, so Dirichlet algorithm returns the shortest path. Okay, but hmm, and you will save the cost difference in between, like, correct, in the edge. What is the cost between 0 to 1 difference, absolute
Yes,
difference?
yes, sir. Absolute difference will give weight.
Okay, absolute difference will be the weight for this, and then shortest path. And then you have to check the condition also. Okay, so that based on the condition you have only connected one step and two step. So, but I think for the big input, your graph will become actually very complicated. Okay, so you can also think about that approach. You can come up with the solution. So yeah, it is looking interesting. You can think for this how you can convert this information to the graph and then the STL quota. After that, just think about the so the time, what time your algorithm is taking. Okay, so
Time
that is the
complexity, sir.
time complexity. Because solution, definitely we can solve this problem in different many ways. You can solve this with the help of recursive approach. Okay, and so you have to see, but you have to check the complexity. You have to calculate the complexity for that. If you have any solution.
Excuse me, sir. We can use the dynamic programming approach for this, right?
Yes, so that we will discuss here. So any idea for the DP approach, how you will apply the DP approach here? So I'm asking.
So we'll use the DPI to represent the minimum cost to reach the stone I.
Okay,
So
DP.
DP0 will be equal to 0 because the cost to start at the first stone is 0.
Okay,
For
yeah,
each stone,
fine.
for each stone I, the frog can jump from stone I plus 1 or stone I plus 2. So the cost
So
will
that
be,
DP table you are maintaining for the each stone, correct?
yeah.
Okay, so we have 4 stone here. So let me just take the information like you have
Okay.
4 stone 0, 1, 2, 3, and like you are storing 0 for this value, correct? Okay,
Yeah.
so DP0 is 0 now. Then
DP0 is 0. Then
hmm,
for each stone I, the frog can jump to stone I plus 1 or stone I plus 2.
hmm, okay.
If the frog jumps from I to I plus 1,
Hmm.
the cost is DPI plus absolute. Can I share the code, sir?
You have put the code.
Yeah, I got the code. Can I share it?
Okay, you can send me. I'll share in my screen. Then you can discuss. In the chat, you can paste. Okay. Okay, so this is your code. So what you are doing, you have created a so if I am equal to 1 dp cost. Okay. Okay. So if n equal to 0, if there is no stone, you are returning a 0 answer. Correct. This is fine. And then 1. If n equal to 1, what n is representing here? So is the length of h. Okay, empty for 0. Okay. This is okay, n equal to 1, 1 stone is there, so 0. Okay, then what you are doing, you are just including the infinite value for each place, n place. Okay. Then dp0 is 0. Okay. And for I, can you explain now what you are doing, Balakrishna? Your mic is off.
Yes, sir. Yes, sir. Yes, sir. So,
Uh-huh.
if frog jumps from I to I plus 1, the cost is dpi plus absolute of hi minus hi plus 1. So, that is the frog. The stone from each stone I, the frog can jump to stone I plus 1 or I plus 2. So we
Okay.
calculate the cost for each possible jump and update dp accordingly.
Okay, so for I in range n, so I, if I plus 1 is less than 2n, okay, it's index, and then you're taking dp I plus 1, mean dp of I plus 1, what is the current cost, and then dp I absolute value of hi minus, okay, hi minus hi plus 1. Okay, I, this is the I you're taking, and I plus 1. Okay, and if I plus 2 is less than equal to 0, then you are filling this also. In dp of I, hi, okay, hi, and what is the I plus 2, and returning dp minus 1.
Sir, you can delete that h eval input and print min cost at the end.
This is the, yeah, looking correct. Okay, so this is the correct approach to test his pass. So here actually this is also fine. You are filling by the two condition. Okay. When I will become 2, then again this will be updated. Yeah, this is also fine. Yeah, this is correct approach. How we are discussing this. Okay, so okay, let me discuss the approach again. So same things we are planning to do in the DP approach. So what we are trying to do here. So when we are filling this, so first thing, because we will just try to apply the DP approach here. So we will just start with the sub problem. Okay, so small problem. For the given same problems, we will think what is the solution for a small problem and how we can use that solution to find out the overall solution. So dp0, so this is the indexing which is given. Okay, but -1. Okay, so you have created the another type way. You have created one more index. So like this. And it is over 4 here. And initially you set this CP equal to 0. So this is indicating that if you have total n stone, if there is no stone, okay, so dp 0. This dp0 is representing if there is no stone. So what will be the solution for that? Is there any cost? No. Just think about if there is no stone and we are just asking this problem, then there is no cost. Correct? Zero cost we are taking directly. If we are just thinking about that, if we have no stone. Then for the one stone, suppose if we have one stone, so this is just check the code again. dp0 equal to 0 and infinite we are filling. Okay, so why we need this infinite? Okay, so that is fine. Okay, so then we will just calculate the cost for here. Okay, so that one cost, this point, what is the minimum cost required to come at this point? Okay, so that value we will calculate. So here I can come from only this point, so like this position. Okay, so like 0 to 1. Okay, suppose if I'm taking that this is the first in that stone. This is the first stone. 0, 0, 1, 2, 3, and our that value was like 10, 30, 40, 20. So 10, 30, 40, and 20. So if I am at second stone, so what is the minimum cost to reach at that one index stone? Okay, so that value we will store here at this place. So at second stone, suppose just imagine that there is no stone after that. This is the final goal. Okay, so 0 and 1. This is the 10 and this is the 30. So what will be the minimum cost for this to reach at the final this stage? Okay, so 0 to 1. So you have only one choice here. So you can directly jump from 0 to 1. Okay, there is no option for that. You can directly jump. And what will be the cost for this is? So you can calculate the cost. What is the minimum cost here? So just take 10, this 30 minus 10, so total 20. So 20 cost will come here because this is the one option you have directly. Okay, for this location. Now you have the solution for if you have only one stone. Okay, that only suppose if you have this 0 stone with 10 height, and this is the same source and this is the same destination. So there is no cost. 10 minus 10, 0. But if you have like 2 stone, then 10 and 30. So you need one step from 0 to 1. Now just increase the size of this problem. Now you have this 3 stone, 0, 1, 2. Okay, 10, 30, and 40. So what will be the solution for here? 2. What will be the solution till 2? So here you can come from either 0 to 2 or 1 to 2. These are the two possibilities. So at any position, you can come from either just adjacent, okay, previous adjacent, and previous adjacent to adjacent. So this is the two positions where from you can jump at this point. Okay. So now we will just get a minimum solution till the previous solution. Okay, previous stone. What was the minimum steps required till the this previous adjacent stone? And what was the minimum cost required to this adjacent to adjacent previous? Okay, so that we will check which one is the minimum, and then we will add the next cost. So in this way, we will just find out. So previous cost at so cost we are saving in this DP array or list. We can say that this is the cost. Now, if I am jumping from this 1 stone to 2 stone, so what is the cost? Okay, what is the cost? 40 minus 30. So this is the cost. And to reach at the previous stone, what was the cost? 20. So we will add this 20 plus this is the jump cost from this position. Okay, so 20 plus this 10. So this is the one possibility I am getting. Another possibility I have, if I'm that frog is jumping from 0 to 2, this position. Okay, so then I'll just calculate the difference, absolute difference between this 40 and 40 minus 10, and what was the cost to reach at the previous adjacent. Okay, so this 0 adjacent, so that was 0 only. So plus 0. So out of these two possibility, which one is the minimum actually? Okay, so what is the minimum among all these two possibility to reach at this point? Okay, so 20 plus 30 is 30, and this side, this is also 30. Okay, so I'm getting 30, 30 both. So this will be the solution till this point. Okay. So that means I'm calculating the solution for each small problem one by one. Okay, like this. So till 2, the second stone, I am getting the solution, minimum solution. This is the minimum solution. Okay, 0 to 2, I am getting 30 steps at least required. Okay, now just include the one more stone, that is the last stone here. So here same things at third stone. So now just think about the 0, 1, 2, 3. Now I'm looking for this third stone. At this stone, where from I can come? So I can come just adjacent like this too, and from this position. Okay, according to the question. So this is the 2 stone. Then I have already solution till this 0. This is the 20. This is the 30. Okay, so I have the minimum cost at this point. I'll just calculate the cost. What is the cost required to jump from 2 to 3? Okay, so 2 to 3, 2 to 3, and this is the cost which was given at 40 and 20. So 40 minus 20 is 20. This is the jump cost. Okay, but what was the minimum cost till 2, from 0 to 2? So that we have already calculated previously. So we will directly read this solution. So 20 plus 30, this was the previous solution we had. So total 50. Okay, so from this point to this point, I am getting this 50. Okay, so 40, 20. Okay, yeah. And another possibility is if I am coming from this one index stone. Okay, so 1 to 3, like this point. Then what will be the cost? So 1 to 3, what is the jump cost? Is 10 and 20. So that is difference is only 1 to 3. If I'm jumping, so 10 minus 20, so that is 10. Okay. But what was the solution till 1? This is okay. So we will not calculate again. That we have already done previously. Okay. So we have already find out the minimum cost from 0 to 1 in the previous approach, and we have stored the solution. So 20. This was the previous solution till 1. That we will directly read it from here. So that is 20. And what is the minimum among these? 50 and 20. So this 10 plus 20, this is 30. So 30 and 50, minimum is 30. So we will store this solution at this position. So 30. So this is the final one, and this solution we need to return. Okay, this solution we need to return. So in this way, we can calculate the final solution. For this approach 0 to 3, we need a minimum cost 30. Okay, so in this way, we will think here. So to start with a small problem, and then we will write a solution for the main problem. And we will use the previous solution to calculate the further final solution. So same things now, same approach we will use in the code. So this code is also very similar. So same things what we are doing here. So only the things is in this n equal to 0. So we are just getting directly, we are returning a direct result here. If there is no stone, then we are returning 0 answer. If there is one stone, still we are returning 0 answer. So, okay, so this is the correct solution. Okay, or if we have no stone and one stone. After that, we are calculating this. We are filling all the value infinitely of all n place. Okay, so 0 to that we are calculating this matrix, and all place we are filling infinite. and then we are setting dp0. Okay, so dp0 equal to 0. So that is the one thing we can directly fill. After that, what we can do, we can also fill, like I can just little bit modify this to make more simpler. dp1, what we can do directly, so I can write, because this is also a simple one step solution. Okay, so abs, and here I'll just write a dp. What is the solution? So what is the height actually? So that h and h1, so h0 we can write 0 also, so h0 minus h1. So this is the direct solution we can write for dp1 also. Okay, so if there is only one stone, 0 cost, and if we have added one more, so we can directly jump. So what is the cost for that? Simply calculate the absolute difference, one step. Okay, after that, what we can do, we can set a range for the here. So like we have already done for dp0 and dp1. Okay, two places I have already calculated. Then we can start from 2 index. Okay, 2 to n minus 1. So this range we can run here, and after that we will just simply check and we will fill the current I position. Okay, so that we can do like so dpi. Okay, so we are looking only for this I, what I will start from second index, and to fill this we will simply write minimum of dp of I minus 1. Okay, so I minus 1 and plus. Okay, so I'm just thinking that I'm jumping from the just previous adjacent. Okay, I is the current adjacent we are looking for. What was the minimum cost for the previous adjacent stone, and absolute difference between this two places. So absolute difference between these two places, so that is h I minus 1 and minus h I. Okay, so this is the first possibility, and second possibility is just a looking for the second adjacent. So that is I minus 2 and jump from I minus 2 to I. What is the minimum amount both? Okay, so minimum of both possibilities. This is the first possibility if I'm jumping from the previous adjacent. Okay, and this is the previous second adjacent. So,
Sir, that bracket should come.
bracket is
Yes.
not proper.
It's a dp of after dp of I minus 1. There is a
One
that-
second.
this bracket is
DP, okay, yeah, this one. You have to put one more, or we have to remove this. I mentioned absolute, and this is okay, and this, okay, this is also, I think. Now fine? I think now fine.
yes, sir.
And after that, we will return this dp minus 1 solution. So let me check if it is working or not. Okay, failed. So what was the error? INF. Min of this dp. Okay, so dp1 is, I think, state 1 is 0. Internal things. Okay, what mistake we are doing? We are creating a matrix 0 to into n. This is fine. TP1 we are filling it with H0. H0 minus H1 is also fine. I in range 2 to n. Okay, 2 to n and for I. Okay, this condition we need to. That infinite will also work, so no problem. Okay, so this is the approach for the first problem. Okay, I hope this is clear how we are solving this problem. Any query in this first problem?
Sir, what is the time complexity?
So time complexity, so just look about here. So we are running only with this single loop. Okay, so we can just try the complexity, we go this n.
Yes, sir.
Okay, so in this way, we are simply calculating this information, only we are running a single loop and we are calculating our steps. So this is very optimal solution or efficient solution in the order of n time.
Sure.
Hmm?
Sir, that using Dijkstra's algorithm also worked, but that complexity is little bit higher.
Yes, definitely it will be higher. Because that graph will be converted into a edge and vertices. Then that is the first task is the conversion. Then we have to apply the algorithm, and it will be done. So
No, so the
that will be the
conversion
costly.
of n, but the Dijkstra's algorithm is more.
That will take more time.
But
But yeah, definitely. But you can try that approach. Okay, you should know how the problem can be solved in the different way also. Okay, any other query? Anyone else? Is this clear? How we calculated the solution? If any part is not clear, you can ask again. Lisa, any other?
Sir, could you please explain from for loop?
This for loop? Okay.
Yes, sir.
Okay, I'm just explaining here. So what actually we have done in the code. So we know that how many stones we have. Okay, so that H list we have and we calculate the length for H, that is actually n. Okay, we are achieving. So for example, in the previous example, this was 4 stone. So for how many stones we have created one list, okay, for the solution. So this is list we have created for the solution for the sub problems. So now 0, 1, 2, 3. This is indicating that DP, if we are giving the name for this. So if we are filling any value for 0 index, so that is the solution from 0 to 0. If we are assuming that we have only one stone. Okay, so 0th stone we have, and there is no stone after that. And so any height is there. If suppose the height is 10 for this stone, and our frog is at this point. So there is no final last stone. So this is also a last, and this is only a first stone. So that it is not required any jump for here. Okay. So what will be the solution for this? Is there any cost required here for jump?
No,
Okay,
sir.
so no. So if you calculate also, suppose if you assume that this is the first and this is the last, and because if you calculate the absolute difference, so 10 minus 10, you will get a 0. Okay, so 0. So we are just filling the solution for the sub problems, okay, or a small part of the problems. We are assuming that what is the solution if we have only one stone. So that solution cost will be 0. Okay. Then we are just adding one more. Okay, now we are assuming that we have 2 stone only. Okay, so 0 and 1. So what will be the cost? Then we are calculating the solution for DP1. Okay, DP0 we have directly put. DP1 we can also put directly because if we have two stone, then there is no constraint required which is given, because we have no choice. We can only jump in one step, okay, without skipping 0 to 1. This is the only choice we have. So we will simply calculate the absolute difference of the both stones. Suppose the height is, suppose this one index is like 20. 20 minus 10, that value we directly calculate, and we will fill the value. Okay. So absolute difference between the height of H0 and that height of this one index stone. So what is the difference between? So that we will calculate like this: H0 minus H1 and absolute difference. Okay. So what is the absolute difference? So we will directly fill this also. So same things we have done in the example. So that is now filled by 20 for this example. So these two steps we have done in the constant time. Okay, in the fixed single step. But after that, we don't know how many stones are there. But from this position, now we have two choices every time. Okay. Now we will calculate the solution for this second index. What is the minimum cost required to reach from 0 to this 2 index? To reach at the second stone, where from we can jump. Okay. So the condition was given that if a frog can jump from I to I plus 1 and I plus 2. So that things we can think about the reverse. So to reach at this stone, where from frog can jump. So either it can jump from the this last just previous location, okay, in the one step, or it can be jump from previous to previous location, okay, in 2 steps directly. So we will just look for the solution. What is the cost to jump from the previous, and what was the solution? What was the minimum cost solution till that point? Okay, so we will not calculate again that part. So what is the previous cost? We will not calculate again. So we are calculating the solution for from a small sub-problem, and we are storing the result. And we are using that result to calculate the solution of the next part. So same way, so what was the stone height at the previous step and the current step? So we will just calculate the absolute difference, and we will add the previous minimum cost on that step. So that is actually a solution from 0 to that point. And now we are adding one more step to reach it to the next step. So that calculation we are checking here. So to from DP 2, and after that each position. So we will always check what is the solution for DP last 1. Okay, so from at this position, I can come from this last position. Okay, DP1, this plus absolute difference of that H of the 2 minus or H like 1. Okay, this is the one possible solution to reach at this position. Another solution is I can jump from 0th index. Okay, so DP 0 plus absolute difference of H2 minus H0. So this is the two possible jump, okay, from the frame. And among all these two possible jump, what is the minimum cost we are getting? So that solution we will store as a final solution, because our final goal is here to find out the minimum cost. So among these two possibility, what is the minimum value? Okay, so we will store here. So that we will get the solution from 0 to 3. To next position, we will check. So suppose this is the next, suppose I am getting I. We will check I minus 1 and I minus 2. So from I minus 1 and from I minus 2 to reach this. So at every steps by the code, actually we are just following this approach. And you can see from for I in range 2. Okay, so this was the next step we are calculating. And for each I, we are just checking what was the previous minimum cost, I minus 1. Okay. And after jumping from that location, so what was the absolute difference? We are adding this and comma the previous to previous. So because that frog can jump from I minus 2 also. So that what was the cost till that point, and from that point to current this I point, what is the absolute difference? Okay, that we are adding. So among all these two, what is the minimum that we are storing at the current position? So in this way, we are calculating the minimum cost for each point from 0. And our final goal is here to find out the minimum cost to the n minus 1 store from 0. So then that solution we will get at the dp n minus 1 index. So that we are returning here. Okay, so dp minus 1 is just also indicating to dp n minus 1 index, last index. Okay, last store.
Okay, sir.
Okay, so in this way we are following this.
So with memorization also you can do it.
Memorization you can do, or you can also do with the recursion without memorization also. Okay, all approach you can apply here. But this is the most efficient approach, because if you have use that memorization things, if then you will use the recursive, correct?
Yes, sir.
So then that will increase the cost only for this recursive cost, recursion, internal cost. So this is, I think, the best solution.
Efficient.
Efficient. Okay. Yeah. So I hope this is clear. Can we move to the next?
Yes, sir.
Okay. So this is the another problem. We have count subsequence. So I hope you know the subsequence meaning. That algorithm you have also seen in the week 9. Find out the subsequence, common subsequence. Okay. So here a subsequence is a sequence that can be derived from another sequence by deleting some elements without changing the order of remaining elements. Okay. So that is also very important things. You should know the meaning of the subsequence. Okay, so subsequence means, let me take any string. So A, B, C, D. So what are the possible subsequence here is like A, C, D. Okay, so A, C, D, we can take as a subsequence. B, C, D, we can take as a subsequence. So B, C, D. So in the subsequence, actually, order should not be changed. What character we are just taking as a sub string or something, but that order should not be changed. We can remove some characters from in between. That is called as a subsequence. So here A is also a subsequence. If you are taking AB, that is also a subsequence. AC is also a subsequence. AD is also a subsequence, because or D is coming after A. Okay, in the original string also. So that actually the property should remain same. We cannot say that CB is the subsequence. Okay. So this is not a subsequence because here order is now changed. Okay. Here B and C is coming after B, but here is coming before it. Okay. So that becoming wrong. So that is the definition of substring, which is given in the question statement. And after that, write a function count subsequence that accept a string s which contain only digit characters. Okay, so here we have one string, but that containing digits inside the string. The function returns the number of non-empty subsequence that can be obtained from s such that every digit in the subsequence is strictly greater than all previous digits if exist. Okay, so here this example is given. Let's take and understand that 7598. So 77598. So what substrings we can take? So if we are taking one digit, so no need to comparison. So we can take all single digit like 7, 5, 9, 8. Okay, so this is called as a substrings possible. Okay, if we are taking more than one digit, okay, like 7, if we want to take 7, 5, then we cannot take. Okay, so let me read again. So what is the condition? Non-empty subsequence that can be obtained from S such that every digit in the subsequence is strictly greater than the previous. Okay. So if we are taking like 2 digits, 7, 5, we cannot take. Hello.
Sir, why we are not taking 7 and 5?
Excuse me, sir. Can I share the code?
Yeah, Balakrishnan, just give me a 2 minute. Just important call.
Okay, sir.
Yeah, sorry about the interrupt. Okay, Balakrishnan, what you are saying?
Sir, can I share the code?
Yeah, you can share in the chat. So in between, I'll just discuss the another query. So this I think just interrupt in between. Why we cannot take 7.5, correct?
Yes, sir.
So according to the person, it is mentioned that in the subsequence, every digit should be greater than to the previous digits, strictly greater than. You can see in the question statement, such that every digit in the subsequence is strictly greater than all the previous digit. Okay. So this condition we need to fulfill here. Actually, if so suppose if we think about 7, 5, we cannot take this because here this this 5 is not greater than the 7. We cannot take this. But 7, 9 we can take this. Okay, so here 9 is greater than 7. So this is okay. 7, 8 we can take. This is also okay because 8 is greater than 7. And next, suppose if you're taking like 5, okay, so 5, 9. So 5, 9 is also possible because this is also correct. And 5, 8, this is also correct. Okay, so it is also fulfilling the our criteria. 9, 8 we cannot take, okay, because 8 is smaller than this. And also we cannot take more than 2 length because if we take 7, 5, 9, then it is not following the proper rule. 7, 9, 8 we cannot take also, okay. 5, 9, 8 we can also not take because in between this 8 is now smaller than 9. So in this type of combination in the given order, what are the possible combination we have? We need to calculate this. So you can count here. So 1, 2, 3, 4, 5, 6, 7, 8. Total 8 substring we are only able to count, which is following the rule. So I think this is the same answer given here. Okay. So which is following the rule. So now here you can also see. Here we have to check the all possibility. Okay. To calculating the final solution, we have to figure out the all possibility, all solution. Okay. Then we can only find out. So what how we can do in the uh, smarter way with the help of TP. So one solution is posted by Balakrishnan. Let me just use that and to see how that approach is working. Okay. Yeah, Balakrishnan, can you come up the approach, what you are trying to do here?
Yes, sir. Just a minute.
Hmm.
Yes, sir. I just created a DP with 0, 10, and for each digit for every scene for all scenes, I made the digit as integer. Then I initialize new count to 1, and for every digit, uh, I loop through the new count, and then the sum, the DP, I did the sum. That's what I did. Yeah.
But how it is actually getting the solution? I'm not getting this 7 and 8 line. What is this DPD is representing? What is the new count equal to 1 is representing?
We initialize DP to store the number of subsequences ending with each digit. Then, as we process each digit in the string S, we determine how many new subsequences can be formed by appending this digit to all smaller digit subsequences. Then the sum of all elements in DP gives us the total count of valid subsequences.
Okay, so for each digit you are calculating this.
Yeah.
Okay. So for explanation of this code, I'm assuming that what you are trying to do, you are maintaining one DP table, and that DP table is maintaining the index for like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct?
Yeah.
This is the total index, and you have initialized the value for each is 0.
Yeah.
At the first step. And after that, your code. So for C in S, okay, so you are just reading each that character of the string.
Each character.
Each character, but that character is actually a digit. So you are directly casting that in the integer. Okay, and new count equal to 1. So you have added this one count, new count. Okay, so you take this variable. We can do directly like +1 on this thing. Okay, at the last. Okay, so this is for D in range digit. Okay, digit. Okay, what digit we are getting? Define. Okay, to new count. 0 to 0 to that digit you are calculating, and then plus adding. Okay. Digit. You are adding new count plus equal to DPD. Okay, you are adding all the solution by this loop. Okay, fine. Okay, so what we are doing, suppose we have this 7, 7, 5, 9, 8. Yeah, this is the final approach. So what you are doing, you are reading this first digit as a 7. Okay, until 7, because this is the first string you have. First character you are reading here 7. So you can see, so this table we are maintaining that how many the subsequence we have formed, okay, with the help of that given digit. So we are considering this index as a digit. Okay, so 0, 1, 2, 3, because every digit in the strings can contain only these number, okay, either 0 to 9. So we will just look at till that digit, how many strings we have done, created, okay, how many subsequence we have created for that. So 7, if you are taking 7, so we will look till 7, so 0 to 6, okay, 0 to 6, how many total substring we have already done. So you can see there is no string, 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So all are 0. After that, we are adding 1 plus, because we are taking this 7 as a 1 character. So 7 is coming, is the next. So till 7, there is no solution we have done. Okay, there is no solution we have done. And for 7, actually, we are getting the first substring. So because of that, we are adding all the value from 0 to 6 first, and then plus 1. Because this 1 is coming by this, including the 7, okay, as a substring. So this is just indicating that we are creating one substring with the help of this 7 till now. Okay, so we will update this value by 1. Okay, so this will become 1. So now this is indicating the one solution. If we have taken this first digit, so this is indicating that we got a one subsequence, okay, for this digit. Okay, and this is the optimal solution. Suppose if you have the solution, if you have only this substring, if this is the only string, then what will be the output answer for this? Only one. Okay, so for this string we have only one character, so we can create only one substring with the help of this one. Okay, so we have stored the solution for this 7. Now let's take this 5. Okay, so let's take this 5. Now for 5, okay, so for 5, if you're taking this 5, also we are taking this indexing in the increasing order. Okay, this is also following that rule which is given. Okay, so which is given as a in the question statement. That means every digit should be greater digit should be come after the smaller digit. So that order we are getting in this order. So let's, if we are taking 5 is the next. Okay, if you're taking 5 next character, so that is actually indicating this 5 digit. Okay, 5 digit. But this is smaller. So what we are seeing here. So we have already updated the solution for 7, but after that we are getting a smaller one. Okay, so that will not affect the previous output for the 7 because this 5 is smaller than 7. Okay, so 5 is smaller than 7. So if this 5 is coming after 7 in the string, so that cannot make as a subsequence according to the question statement. Okay, so 7, 5 cannot make the subsequence because this 5 is smaller than 7. So that will not affect the answer, but we will calculate the answer for this 5. What is the solution for 5 we have? Okay, if we have only this 5 as a single character. So we will do the same things. We will check the previous solution, what character we are getting before that. Okay, so if we have, what solution we have before that? 0, 1, 2, 3, 4. All have 0 solution, 0 subsequence. Okay, so we will add both all and then plus 1. So that if we are considering this 7, 5, so that means we are getting this one from here. Okay, so for this one. So this is indicating that we are also getting one more subsequence. That is only for 5. Okay, we got one subsequent that is only for 7. Now move to the next. So 9. Okay, so 9 is, now we will check what are the maximum solution we have for the 9. So for 9, you can see this is the point 9. But this 9 can make the solution with the previous smaller value, that digit. Okay, and how many subsequence we got till the previous digit, so that we will calculate for each. So 0 plus 0, 0 to 8. Okay, so 1 plus 1 we are getting here. Okay, so if we will add all these values, so 1 plus 1, 2, and 1 for this single 9. Okay, then plus 1. So total 3, it will become 3. How we are getting this 3? Because one single 9 will be considered a subsequence and one with this 7. Okay, so that we are getting the solution from here. Okay, so one we will get like this 7 and 9. Okay, we are getting this information. One we are getting with this 5, 9. Okay, so 5, 9. So total 3 solution we are getting. If we are considering this 9 inside the solution. So 3 we got when we included 9 also. Okay, now the next digit 8. If we consider this, so you can see 8 is this one. And till now, how many subsequence we have got which, by the digit which is coming before this? So only 1 plus 1, and 1 is the single 8. So that is also become 3. So 3 is the single 8, and 1 with the 7. So 7, 8, and 1 with the 5. Okay, so this 5, 8. So total 3. Now these things we have done with the all digit. To find out the final solution, just add all these values. What value we are getting? So sir, 1 plus 1 plus 3 plus 3. Total 8. Yes.
Sir, for this 8 and 9, you should also consider 5, 7, 8, right?
No, or you cannot change the order, no? In the main string, you can see
Okay.
5, 7, 8 you cannot take because 7 is coming before that. Okay, so because of that, this is calculating smartly. The last digit is only checking for the previous digit's solutions. Okay, any digit is only checking the solution with the previous digits, which is coming before that. If the digit is smaller than. Okay, so because of that, we are considering this sequence as the increasing order, 0 to 9. We are only looking the digit which is coming before that. So that can be include the subsequence.
Sir,
Like this. Yes.
so you said that 578 is not possible because in the given string it is not. If it was in the given string also, if 578 was that order was there, then it should come, right?
587. You are saying that if that constraint is not there, so like
578.
this. 578 we cannot take because this is not a subsequence.
No, sir. If it was subsequence, then that should also be counted. Right?
No, I'm not getting your query.
No, sir,
So what you are saying?
if it was 578, then 578 should get counted.
Okay, you are saying that if string is 578.
And maybe some other digit.
Okay, fine. So let me take some example for this also. So like 3 and 9, like this. Okay. So how that solution we will get. So just do the same thing. So like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So initial solution is 0 for all. Then if we take 5 digits, so 5 will create, because this is a single digit, okay? And till now, there is no initial character we have before this. So because of that, all solutions are 0. Okay, and till 5, this point, what solution we have? There is no digit before this. So because of that, all are 0. So we will just count a 1 plus what is the solution of previous one? 0 plus 0 plus 0 plus 0 plus 0, and then plus 1. And that plus 1 we are calculating, just considering a single digit. Okay, so now it will become a 1 by the first digit. When we will take 7, so this is coming in the string and also coming after this 5. We have already done this 5. Now to calculate the solution for this 7, so that is actually 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 0. So total 1 and 1 for single this character. Okay, so now this previous solution is just giving this information that we can create one solution with this 5 for the 7. Okay, so that means now we got a 2. Okay, so one is the 7 and one is 5, 7. You can understand this. 8. So for 8 to fill this, so how many solutions we will get? 0, or we will add all. So 1 plus 2, 3, and plus 1. That means 4. So 4 solutions we will get with this 8. So what are the possible 4 is 8. Okay, and 2 we have combination, we have till 7. Okay, so that combination are actually 7 and 5, 7. Okay,
So can
and
you
we
repeat?
can so when we are just taking this 8, so one solution we are getting as a single 8. Okay,
Yes,
but
sir.
before that we have 2 solutions till this 7. Okay, so 7 we have 2 solution possibility. If we combine this 8 with these 2 solutions, so you can see 7 and 5, 7. With this we can also put 8. So you got these 2 possibility. Okay, and one possibility we can directly take 5. So that is actually 5, 8. So total solution we got 4. So you can see this we are getting 4. So this information we are getting that till this point 7, how many? So this 7 actually how many solution is subsequence this is contributing. So this is contributing to subsequence. Okay, and that we will include with this 8. So 8 will come after this. So that will produce 2 subsequence. Okay, and one subsequence we will produce with the 5. Okay, so because 5 is creating one subsequence, and with this we will also get a 1, 8. You include this 8. You can see all are following the rule. So 7, 8, 5, 7, 8, and 5, 8.
Yes, sir. Okay.
So now 9. Okay, so that is the next. Okay, so this 8 is done, and 3. Now 3, you can see 3 is coming after that. So because of that, this will create only one subsequence as a single character. 3, because before that there is no small digit is coming. So that we cannot create. So 3 will create only 1. So this will update 1. Okay. Now next is 9. So you can see this will create many sequence. So because this is coming here, until now, how many solutions we got? 1 plus 1, 2 plus 2, 4 plus 4, 8. 8 plus 1, 9. Okay, so 8 plus 1 as a single. So total 9. This is created. So what are the 9? Actually, we have single 9. Okay. This 4 combination 8. Okay, so these are the combination like 8, and, yeah, 8, and 7, 8, 5, 7, 8, and 5, 8. Okay, and we can include 9 with all. Okay, so now this becomes a solution, and 2 solution we will get with 7. Okay, so 7 solution was this one. So 9, and next solution we will get this. So 9 we have already done. So that 7, 9, and 5, 7, 9. Okay, so you can see 2 solutions we have picked from here, and we put the 9 with this. So 2 solutions we got. 1 we will get with the 5, so 5, 9. Okay, 1 we will get with the 3, 3, 9. Okay, so all are fulfilling our property. So you can see all digits are greater than to the previous digit. So that you can see how many we are getting: 1, 2, 3, 4, 5, 6, 7, 8, and 9. Total 9 subsequence we are getting when we included 9 digits. So that is 9. Now overall subsequence, we will add all these. So 1 plus 1, 2, plus 2, 4, plus 4, 8, plus 9, 17. So 17 subsequence we will get from this string that are fulfilling this criteria. In this way, we are utilizing the previous solution, and we are adding that solution to get the next. Okay.
So
So
if
same.
it is 1, 2, 3, 4, then all should come, right?
So 1, 2, 3, 4, you will get like a, so for 1 there will be one solution. Okay, for 2 you will get a 1 plus 1, 2. Okay, for 3, so 1 plus 2, 3 plus 1, 4, and for 4, so 1 plus 2 plus 4, 3, and 1 plus 2, 3, and for 7 plus 1, 8, like this. And after that, this will be the overall solution. So 1 plus 2, 3, 7, and 15 total. 15 combination you will get for this. Okay, so 1, 2, 3, 4. Then you can make more combinations. So like 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Okay, so like 1, 2, 3, 1, 3, 4, 2, 3, 4, 1, 2, 3, 4. Like this. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Anything? One missed? Yeah, principal. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 2, 4, 3, 4, 1, 2, 3. Okay, 1, 2, 4. Okay, so this is we missed. So 1 to 4 we have missed. So total 15 possible solution we are getting like this. Okay. So this is the solution, and the code is actually doing the same thing what we have discussed. Okay. So we are just using this counter. So for C in every character, we are just converting that into a digit. The digit conversion is okay. So for the indexing, okay. So digit, and then we are just using this one new count equal to 1s, and 1 we are started because definitely for one character will make definitely one substring. Okay. So because of that, we started with this one. After that, we are just reading the all solution till that digit. Okay. What was the solution before that digit? So we are adding that previous solution, and we are getting the final count for that digit. So that we are doing, and after that we are sum up. We are adding the all solution in the DP. That is the result for this. Okay.
So DP of each digit will show the number of combinations in which that digit can come using previous.
So yeah, so the value of the DP for each index is actually representing the solution with that digit. How many solutions are available with that digit? How many subsequents are?
Up to that digit.
Okay.
Sir, here the base case is making all 0 for DP.
So that is actually possible if your substring is still you will not get the 0 answer. Okay, suppose if any for empty string you can only get, otherwise if you have any single character then you will get a 1 subsequence.
No, sir, I'm saying whether this method is using dynamic programming.
This method is using dynamic programming because we are maintaining the solution of sub-problems, okay, previous sub-problems, and then we are using directly that
Yes, sir. Okay.
without solving again. Okay, so any doubt in this? Anybody, anyone? So these two problems were based on the single dimension. The one problem you can think about the coins problem. I think that we have discussed in the week 7 when the greedy approach cannot be give the solution. So let me just discuss that. You can try the solution for that. Okay. So suppose if you have the coin that some coins value. So like you have 10. Okay, and 5, 4, 3, 2, 1 like this. Okay, you have this coins value, and you have the infinite number of coins for each. Okay, each value, and some amount is also given. Okay, so suppose like 25 amount is given. So what are the minimum number of coins required to achieve this amount? Okay, 25. So how you can get this answer? So we have
So can you
discussed.
repeat?
So we have some coin value. Okay, so we have coins actually, and the value of coins is this 10, 5, 4, 3, 2, 1. And each value coins have the infinite number of coins. Okay, so that means we have infinite number of coins for 10 value. Same for 5, same for 4. So we can take any number of coins. Suppose if we want to take, we have the amount 5, we can take 10 into 5. Okay, 5 coins for 10. So then we can get this solution 50. So this type of that information is given. You have that these value of coins in the infinite numbers, and some target amount is given. So the question is, what are the minimum coins are required to achieve this amount by the given amount value? Okay. So how you can think the solution approach for this? You can
Minimum
try
number of coins, sir.
minimum number of coins.
Okay, sir.
Okay. So just look this manually and just tell me what is the solution for this. So we can achieve this 25 like this. So 10, 10, 2 coins we can take. Okay, so that is we can achieve like 10 into 2. 2 coins is required. And after that, only 5 amount will remain. So that we can achieve by the single coin. So 5 into 1. That 1 coin. Okay, so 5. Total are 25. Total coins are 3. Okay. So this information we are getting like this. So same information will be given and you can calculate the solution. So first look what type of solution you are applying here to calculate this.
So we have to return the minimum number, right?
Minimum points.
So then if there was 25 coin, then minimum would be 1, right?
So if suppose we have the 1 coin of the 25 value, so we can directly take 1 coin. But here we don't have, so we will just take this like 10, 2 coins for the 10 and 1 coins for the 5 for this. So like this example, let me take, suppose if I'm taking 45. So you can see again, suppose 44 or any other amount. So we can directly take 10 into 4 and then 1 coin of the 4. We are getting the solution. Okay. So looking like we will always try the highest amount coin. Okay. And try to fulfill the maximum amount by that. After that, what amount is remaining, we will check the next highest amount. Okay. And then we will try to fulfill this. So in this way, we are just, this is the first approach generally comes on the everyone mind. So we can apply here because this type of example, it will looks okay. Okay, you can take most of the example will be fulfilled by this. So like 56, how you can achieve this 56? So you can take like 10, 5 into 10 and then 50, and for 6, you can take 1, 5 and 1 this way. Okay. So after 5 point, only the 1 amount will remain. You can fulfill by this last one. The total 5 plus 2, 7 coins are required. Okay, so that is looking like we will just sort the coins value and just pick the largest amount coin and try to fulfill by that. Okay, after that remaining amount, we will again pick the largest, second largest, and try to fulfill by that. But suppose if this is the case, so 10 and then 8, then 7, then 1. Okay, now this is the case, and we have this coin value, and now I am asking the value for 15. Okay, now what is the 15 value? What is the minimum number of coins required? Suppose if we apply this approach, previous approach, so that was approach actually greedy approach. That was the greedy approach. But if we apply the same approach here, so now we will get an incorrect solution. So let's fulfill by the maximum amount 10. So 10 we need 1. Okay. But after that 5 amount is remaining, so that we cannot fulfill by 8. We cannot fulfill by 7. Then we can only fulfill by this 1. So that 1 into 5. Total 5 coins are required for this. Okay. So then means total 6 coins are required to get this amount by the previous approach. But we can achieve the solution by only 2 coins. 1 into 8 and 1 into 7. Okay, 15. 2 coins. Here the optimal solution is 2, but by that previous approach, which was looking correct in the previous example, but here for this example, it becomes fail. Okay, so we are getting 6 answer for by that. So we are getting this should be the answer. So in this case also, because now we see this. So in this case, our solution can come by any combination, not just only the sorted one and just pick the highest value first. Okay, so that is not the possibility here. So our solution can come from any combination, okay, of the value. And in this case, now you can think about the DP approach. Okay, so you can try this. This can also be solved by the same single dimensional okay, list. Okay, what we have discussed in the previous 2 questions. Same way you can try this. Now move to the next. So this is the like task for you, and now the next next level question actually, that is 2-dimensional. And I think this question is also given in your practice assignment in week 9. This is maximum the knapsack problem. So 9, I think practice assignment. This is the same, I think, the max profit. This is different. But here PPA1 is the same max value item W. This is the same problem. Okay, knapsack. So this is just given in the some story way, and this is one a standard problem in the live coding. So the concepts are same, problem is same, but the some story is different only. Okay, so this problem is popularly called as a knapsack problem, and this knapsack problem is actually a 0-1 knapsack. Zero one. It is written in the question itself also. So this is called as a 0-1 knapsack problem. Another version we have for this is that fractional knapsack problem, and these are the standard problem we have. And that fractional knapsack can be solved by the greedy approach, but this 0-1 knapsack can be solved by the DP approach. So what are the problem is actually you are given weights and value of n items. Put these items in knapsack of the capacity W to get the maximum total value in the knapsack. So means we have this n items. Each item have some weights and value for that. Okay, so some cost or something you can take. And we have some capacity. Okay, so this capacity is represented here as a W, capital W. So that capacity we have, and then we need to pick the items that will provide the maximum value to us. Okay, so how we can select the items from that given items, so that will give us a maximum value for that. Okay. So suppose if you have here 3 items and this capacity is 4. Okay, and each item value and weight is given. So for this example, let me take so we have this 3 item. Okay, so 3 item we can understand 1, 2, 3, and each item have the weight. So weight I am writing here and value I am writing here. Okay. So for first item weight is 4 and value is only 1. Second item weight is 5 and value is 20. And last item weight is 1 and value is 3. So this is just a ID or index. We can see 0, 1, 2. If we are taking index, and this is the information. Now we have the capacity total 4. That means suppose you can assume that you have the box that can take only this 4 weight, maximum 4 weight, and you have these items and you want to take the item from these collection, and that will give you a maximum value. Okay. And you cannot pick the partial item here. Either you have to pick complete or you have to leave that. So suppose capacity is 4, first item is actually weight is 4. So that you can take, but if you're taking this first item, you are getting only 1 value for that. Okay, by picking this 1. Second item you cannot take because that weight is higher than this capacity. Okay, so for this you cannot pick. Next item 1, you can pick this, and here the value is 3. Okay, so the capacity is 4 and that weight is less, so 1. But if you are picking this, you are getting this 3 value, which was the max greater than the previous option you have. If you're selecting 4 and value is 1. So what combination of item you can select? Here, not only 1, you can select the combination of item. Only the condition is you cannot take more than the capacity. Okay, or you can also not take the partial. Then you need to select. So same thing here again. You cannot pick directly. You cannot get the solution directly without checking all the combination. Okay, so here you have to think individual also. And after that, you have to think the combination also. So like what combination I can select? So I can select, like suppose if weight are 2 and this is also 2, then you can also pick this 2 and plus 2. Okay, so then 1 plus 3 will become 4 and capacity will also be less than or equal to 4. So in this way, you have to check the combinations also. What maximum combination you can take. Okay, that will provide you a maximum profit. So in this way, same thing, without just looking at all combination, we cannot get a final solution for this. So same things you have to figure out, but here the information is given more. So here weights are given, and at the same time value is also given. Okay, so that means when you are picking any item, you have to check with the weight. Okay, and at the same time you have to check the maximum value. So that means two parameters are there to combine here. One is the weight as well as the second is the value. So in this case, when the parameters are more, we have, so that type of data generally we maintain in the two-dimensional table. Okay, so like you have already seen in the course problems, that lecture problems, LCS, that minimum array distance, or minimum common subword like this. So where we are maintaining the table actually structure for that. So same things we will do here. So we will create a two-dimensional table for this, and let's see the example for the small, this one, and we will achieve a final solution by the table. So first thing, how many items we have? So number of items we have total is 3. Okay, and total number of weights. What is the maximum weights we have? Okay, 4. So we will check the all possibility number of items and number of weights. Okay, so we will just consider that if we have for each capacity value, because here we also need to find out the combination. So we have the maximum capacity 4, but suppose if we are getting only one item, so that is fulfilling only one capacity. After that, we will get remain 3. Then we have to search the solution for 3. In this way, so we need this information also in the one dimensional. In another side, total number of items, so that we can reduce. So we can reduce our capacity and we can reduce our items to make this big problem into a sub problem, small problem. So that way, so what we will do, first things, we will create a two-dimensional table, and what will be the size for that is, that size will be the, we will take how many items we have. Okay, so how many items we have, so that we will make as a row. So here for this example, so we have this 3 items, so we will create a 4 row for that, and I'll just explain that why we create. And we have the total capacity W equal to 4. So that number of columns we will create one more there. So 1, 2, 3, 4, 5. Okay, this one. So this is for N and this is for W. And 0, 1, 2, 3. And this side 0, 1, 2, 3, 4. Okay, so 0, what I'm taking 0, so we can start with the 0 as a base problem. So that 0 base problem means if we don't have any item. Okay, if we don't have any item, then what will be the solution? So what will be the solution for our problem? So we don't have item and we have the capacity. We cannot take any. So that total value, maximum value will be only 0. So we can fill this row as a 0. Here we are just thinking that if we have 0 items, and this is capacity given as a maximum 4. So for 0 capacity, we cannot pick any. 1 capacity we cannot pick. So all the maximum profit or maximum value we can achieve only 0. Same things, if we are taking capacity 0, doesn't matter what item, how many items we have, solution will remain 0. Okay. So now this is the sub problem we have. Small problems we are just considering as a base problem. So 0 items So it doesn't matter what is the capacity, our total maximum value will be 0. Same things if we have 0 capacity, and doesn't matter how many items we have, capacity, our maximum value will remain 0 as solution. After that, we will just check the solution. Yes.
So can you repeat this base case again?
So base case, what we are taking, we are so this this side we have made the columns in this table for the each capacity value till the given capacity. Okay, so maximum capacity is given as a 4 in the question statement. So we will check for the each capacity till this capacity. So that 0 is possible, 1, 2, 3, 4. Okay, but if person is given, if n equal to any number of items, suppose 10 items are given, but capacity is 0. If capacity is 0 to select, then we cannot pick any item because our capacity is 0. We cannot pick any item, so we will not get any value also. That means our final maximum value will remain 0. Okay, for this case. So because of that, we fill this column as a 0. Same things. So we have taken the all possibility. So here we are just looking the all possible case. Okay, so because of that, we have taken all items, possible items here, and all possible capacity as the two-dimensional form. So same things if our W, okay, so W we have discussed. If our n equal to 0 and capacity is anything, okay, we don't have any item to pick, and we have some capacity. So what you will pick actually? Nothing. So that answer will be 0. Okay, so both case we have filled as a base case. Okay, and we just consider that this is the smallest problem we have.
So row 0 will be 0, all 0 because like 4 times of 0 also will be 0. Value, right?
No, what you are saying? Can you repeat 4 times?
So row 0th row will have all zeros because 0 doesn't have any value.
So this number of this row side actually is representing number of items. How many items we have as an input in the question. So if we have 0 items, what you can pick for the capacity? Nothing. Just assume that you have n equal to 0 information given. Okay, so n means how many items you have to pick. 0, you don't have any item actually. And then capacity is given 4, 5, 3, 6, any capacity is given. But if you don't have any item to pick, then you cannot get any value. Okay, so because of that, we filled all 0 solution for all capacity here, 0 to 4. Same things if your capacity is 0 and you have any number of items, then you cannot pick any item because your capacity doesn't allow you to pick. Okay, because capacity is 0 to pick. So in this case also, doesn't matter how many items you have, then your answer will be 0 for this problem. Okay, so we have taken this 0 to 3 because 3 is the maximum. This is the given in the question. So 3 is given in the question. How many items we have? We are just considering this sample input for this solution. Okay, 4 capacity we have taken as a maximum capacity in the. So that we have created this table. So in this way, we will create a two-dimensional table and we will just look the each possible solution here. Now we will fill this step by step. So like as a column by column. So we will just fill this second. Okay, so that suppose this is the DP matrix. So DP, and we will fill the next step 1 and 1. Okay, so that is indicating to this point. What will be the solution for this subproblem? Now this is the subproblem solution we are calculating. Final solution we will get at this position, last position. Okay, so just assume that you have now 1 item. Okay, so now for this position, what is the value of n? 1. Okay, what is the capacity of this is 1. And that item is given here. So item I am also writing here. So item is just like 0 index because this is given inside the list. Okay, so we will consider that as a 0 index, 1 index, 2 index. Okay, this is the index. Item weight is that 4 and 5 and 1. and this is the weight, and this is the value. So value is given as a 123. Okay, and numbering, because in this table we are just looking like this as a numbering 1 to 3 and 1 to 3, this side capacity. Okay, so this may be create confusion. So when we are just looking n equal to 1, this is indicating the 0th index value. Okay, data. Okay, so that 1 is just representing a counting. Okay, how many items we have? If we have one item, so what item we will consider? Only this item. Okay, which is coming at the 0 index.
Okay, sir. So first
Okay.
item is one, is only
Ha,
considered.
so 1 means one item we are considering from the given items. Okay, that one item we are considering is the first item of the list. Okay, so that is coming at the 0th index in the list. Okay, so both our data is given inside the list. So indexing is started from 0. So that is the required for the code actually. Okay, so inside the code, when we are filling this 1 1, but we have to check the data at previous index. Okay, so 1 we are taking, so we have to check the like 0 index for that. That is just a convention what we are just taking. Okay, so we are assuming that you have only the one item. Okay, so just assume that 0 4 1, this is the item, and you have this W and this is the V. Okay, for this problem you have only one item, and now just consider that you have this weight W. Okay, so can you pick this? If you have capacity 1,
Also,
you cannot pick, correct? So that means we need to check if our capacity, okay, so we are filling this block, so that we are assuming that we have a capacity W equal to 1 only. Okay, for this sub problem, we have capacity 1 and we have this only single item. So what is the overall solution to fulfill this? So to fulfill this, we will always check that if our capacity, okay, if our weight of the item, okay, if our weight of the item is less than or equal to this given capacity, okay, this value. Okay, so we will check always these things like in the as a condition. So if our weight, okay, so this is given as a weight, so weight of this I, okay, we are taking this as a I row and J column, suppose. So I minus 1, okay, because weight is the list where the index is just one less, is less than equal to J. J is directly representing, this index is directly representing the capacity. If this condition is satisfied, then we can only pick the item. Otherwise, we cannot pick. Okay. So in this case, we will directly fulfill Y. We will remain as it is 0. So this by default, this is filled as a 0 as a base case. But initially, we can start with the all 0, okay, to fill this matrix. But we will start to filling this column, okay, so only from this column. But to initialize this, what we can do, we can fill 0 all, but we will update only this positions, this part. Okay, so only this part actually we will update. Previous part we will just read as a previous solution. Okay, so what was the solution for this? Because our weight, item weight is not fulfilling the capacity. So that means this solution will not be updated. This will remain 0. We cannot achieve any value for this capacity one. Okay, so now this is done. Now I'll just move to the next. Okay, so this one, 2. Again, our weight is 4 and capacity is 2. So same thing, this condition is not true. So this condition is not true, then we will not do anything. This solution will remain 0. Okay, so 0 and 0. Then again, next capacity 3. Weight is of the one item, because we are filling this row only. So here we will just assume that we have only one item. So because of that, we are just looking only this single item. So that is now again 0, because our capacity is less than the item weight. This is again 0. But for fourth, this one, okay, now capacity is 4 and item weight is also 4. So this condition become true for this capacity. Then we can pick. Okay, So now we have the choice. So this is the first item we are taking, but when we will fill the second item, so we have to check that if we are just picking that item, what is the profit we have, and so what is the maximum value we are getting. If we are not picking this, then what will be the profit? Okay, so we will think all both the condition. So for this case, what will be the solution? If we have the capacity 4 and we have this 4, so we will pick this. Okay, so like we are just picking this and we will get it. What is that maximum value we will get here? That value we will get 1. Okay, 1. To fulfill this, we will fill value. Okay, what is the value we are getting for this? So this is actually we are getting the solution. So you can see this we are fulfilling, but we will also come up to the that expression. What expression we will put? Okay, so after this row we are not getting the final. Okay, but now come to the next. Okay, so now we will fill the second. So now we got the solution for this sub problem. When we are assuming that we have only one item. Now we checked for the solution for each capacity 1, 2, 3, 4. Now this solution we will directly take in. Okay, we will not calculate again. If any time we are getting any remaining capacity, then we will not calculate again. We will directly pick the solution from this. Now second just include the second item. Okay, now we are looking for the second item. Not only second item, we are just including that. Okay, so that means 1 and this is 5 and this is that 20 value. Okay, so now we have included this. Okay, and we have already calculated the solution for previous one. Now we will check the things. Same things. If we are looking for the item second, so this 2. Okay, what is the weight for this is 5, but capacity is 1. We cannot pick. Okay, so this will remain as it is. Condition is not satisfied. Okay, so in this case, condition will not satisfy it, but because now this is the combination. Okay, so we are just looking at all possible combination. So to fulfill this part 0, now we will check what is the previous possible solution we have and what was the maximum profit for that. Okay, when capacity was 3, previous solution was 0, and current solution also by picking we cannot pick this also, so solution this is also 0, so that maximum solution is 0. But to fulfill this part, that this label, okay, so this part 2 and 4. Okay, second item and 4. So we are not able to pick this second item, but till this problem we can take the previous solution. Okay, so because of that, if we are not able to pick this item, still we will check what was the previous maximum solution we have. So what was the previous solution for this part is, if you're not able to pick this, so we will select the maximum among the previous solution without including this, or what we are getting. If we are able to include this, then what is the solution? So we will select the maximum among both. So that means this one value will remain. We will directly pick the previous solution. Okay. So it is indicating that if we have 2 items, still what is the maximum value we can achieve? We can achieve the maximum value 1 by this first item select. Okay. Second item we are not able to select. So every value is indicating that what is the maximum profit at that point. Okay. So now come up to the this expression what we will write here. So we will write here like this. Suppose this is the DP. And I and J, this we are filling. Okay, so I is indicating to items number. Okay, and J is representing to the capacity. So we will always look the max value, max, and this is the value for value. So this value is the list. Okay, so this value is given as a list for the each item. So value of I minus 1. What is the value for I minus 1? So that means what is the value for this item? Okay. And plus. And we will only calculate this expression if we are satisfying this condition. Okay, if our weight of the item is less than the capacity or equal to the capacity, then we can only select the item. Okay, otherwise we cannot select. So this condition will be written inside this. Otherwise, we will directly pick the previous solution. Not previous, yeah, the previous maximum solution. So, yeah. So that value of item, what item value we are getting? This. And we will add. Okay. So what are the remaining capacity after that? So we will calculate the remaining capacity and what was the solution for that. So solution for that is the dp, and that item we are filling for I minus 1, but the column we will pick here J minus capacity. Okay, so the what was the weight for this? That is actually weight for this I minus 1. So weight for I minus 1. So this is the one possible. Okay. So value we are taking of that item. Okay. And then suppose for this example our capacity is 4 and our suppose this value is 3. Okay. So if we are picking this item, still 4 minus 3, one capacity is remaining. So for that we will look what is the solution for that one capacity. Okay. So that we will pick from the previous part. So what was the solution for the previous part? Yeah. So other this is the one side. If we can take this, and the another part is we will take here dp, and what was the solution without including sorry, I minus 1. So that I dp I minus 1. And that J. In this matrix, so that I minus 1 is representing the previous row. Okay, so previous row. If we are looking for this capacity and our the weight is satisfying the condition, so first we will check what cost we are getting, including the value for the current item, and what was the solution for the previous selection. Okay, not previous selection, the remaining capacity. What was the solution for the remaining capacity? We will check in the previous. Okay, because if we have picked one item from this row, we cannot check. We don't need to check from this because we have selected this item. Then we will check the solution of the previous row only. What was the maximum profit or value we achieved by the previous till the previous items? That we will only look, and we will check only for the remaining capacity. We will directly pick. The another possibility is we will directly check that without including this item. What was the capacity? So among both the capacity, which one is the maximum, that we will select as a final solution till that point. So this is the condition if this condition is satisfied. Otherwise, else part, we will directly write as a dp I and j equal to, and that will be the same previous maximum solution without including this. Okay, so that is directly taken dp and I minus 1 and j. Okay. In this case. So in this case, in this way, this matrix will fulfill each row one by one. We will complete this matrix, and at the last point, you will get a final solution for 4 capacity and 3 row. So this cell is actually indicating when you have 3 items and 4 capacity, which is given in the question cell. So this value will represent the final solution. So if I write the code for that, so you can see what we will do. So same things we will do here. What we have discussed. We need to write this function. Okay. So after that, we will maintain one that dp matrix. So that dp equal to, and we can create this matrix like this. Okay, so this we will use this 0 for we are fulfilling this. that is for the column, so W plus 1, and then for in range, and that is actually n. Okay, weights. So weight n plus 1. So now this will become a two-dimensional matrix, and that will all value will be filled by 0, and number of rows will be n plus 1, and number of columns will be W plus 1. Okay. After that, we will simply run a loop now. So for I in range for this. So we will start from 1 now. Okay, so we will just leave this 0 index as a base case. So 1, 2, n plus 1. For j in range as a W plus 1. And here, okay, so we will simply check that condition. So if so weight, okay, so this matrix name, list name is weight. So weight and weight of, okay, so I is representing 1, so I minus 1. If this is less than equal to j. Okay, so this, if this condition is satisfied, then we will fill our matrix by that formula. So dp I comma j I comma j equal to max of that. Now values, okay, so values of I minus 1 and plus. Okay, so we are directly picking the values from the current item I, okay, from the one less index from the values, and we will also get the solution if any capacity is remaining after taking this item. So that next solution will be available at the DP matrix itself. That is actually j minus. First is the item number, so that we will take from the previous item, so I minus 1. Second index we will fill j minus, what is the capacity for that? Weight. Okay, so weight for that j minus weight for I minus 1. So this is the one possible answer. I minus 1 we have taken. After that, second. So if so, this is the one possibility, and if this is maximum or without taking this, okay. So what is the solution for that? So that we will take like simply dp, and that is I
That
minus
is current value.
Sorry.
No, sir, the other option is the current value itself.
Not current value we are calculating. We cannot
Yes.
take current value. We can take the previous maximum solution we got. So that we are taking from the previous row and the same capacity. What was the solution? Okay. So that is indicating DP previous row. That means till previous item without including this item. What was the maximum solution at we have at this J capacity? Okay. So that we are directly taking. So this is the one. So if we are just this condition is satisfied, so there is a possibility that if we are calculating this solution, suppose we are taking the current item and what is the another item for the remaining capacity we are taking, what is the total cost, total value we have. But if that total value may be the less than of the value, if we are selecting the item from the till the previous solution. Okay, so in this case, you can see if we are selecting the last item, then we are getting the maximum value. Okay, and there is a possibility that you are getting the maximum value by just taking the previous one item. And if you're selecting the current item, you're getting the less value. Suppose just interchange this, just first index value and last index, just interchange this. So you can see you are getting the maximum value if you're selecting the first item. But later, if you're selecting the last 4 value, you will get a less value. So that means previous maximum solution you can directly take in, and you need to compare both. what was the previous maximum solution you have, and what the current solution you are getting by taking the current item. Then what is the maximum value among both? Then that value we will take as a maximum solution. So this is the part when we are considering that when we are selecting the current item and we are just looking the maximum value. Else part is if our current item weight is not satisfying this condition. Okay, so our current item weight is just a higher than to the capacity. So in this case, we will directly pick this dp. Okay, this one equal to this. So current dp of I and j equal to this. dp of I minus 1 and j. So in this way, our complete matrix will be fulfilled, and finally we will return the solution on the last index. So that is actually dt, and that is number row is n and column is w. Okay, so this will contain the final solution with the full capacity and full number of items. Okay, so let's check this. Okay, some error is there. So index error, list index out of range. I, j.
Yes, sir. DP, like, there should be one square bracket before for j.
Where?
In the first line, DP, the list we have said, the matrix.
This one.
Yes, sir. Before for, I think bracket should close.
No, this is not the case. So
No,
we are
sir,
getting the error here.
Okay.
0 for I in range, this is W plus A, and then for okay. So one bracket you are saying here, eh? Okay, this one. Okay, now for it. Yes. So for each row, we have created one column. Okay, nested list. Okay. Yeah, so this is the solution. Let me check the private test case also. Pass. So now this is the solution for PP also. So same solution, we have this knapsack column. And here, this is very similar to the approach which we have discussed in the lecture problems also. It's yes, common this matrix many problem. 3-4 problem we have discussed in the two-dimensional things. Okay, so now the next problem is also very similar. So that can also be solved by same same approach. So this is the problem third. Okay. So in this case, given a rod of length n inch, okay, and n list of price. This is the information given. So what is the length of the rod and what is the list of the this price list that contain piece of all piece of the size smaller or equal to n. Determine the maximum value obtainable by cutting up the rod and selling the pieces. Write a function cut n price and return the maximum value obtainable by the cutting of the rod and selling the piece. Okay. 3, 4, 5, 6, 7, 8. So what is this problem? First, understand the problem here. So let's take this. We have the rod actually, so 8. Okay. Suppose this is the length of the rod. And we have also given the price here. Okay, so that price value is given. So that is 0, what we consider 1, 5, 8, 9, 10, 17, 17, and 20. 17. Just consider that indexing will remain 0, starting from 0, but we will consider it as a 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in this way, so what it is indicating? So it is indicating that the length of 8, if we not cut this, okay, so that means the length will remain 8. If we sell this the same rod without cutting anything, so that cost price is 20. Okay, that price is 20. Now, suppose if we cut this rod, one is 17, that one is 7, and so after cutting the 7, so what will be the remaining length of 1? Okay, so that is the 1. 7 plus 1, we can write like this, 7 plus 1. Then what will be the cost? So this cost is for 1 is 1 and plus 17. So we are getting 18 cost if we sell this after that by cutting this. Okay. So if suppose if we cut this rod as a 4, okay, so 4 plus 4. So the one 4 size cost is 9. So that is 9 plus 9. Okay, so 18. Only 18 value you are getting. So what should be the cut actually? How you can cut this, or you can also cut like this. You can cut of 4 size. Okay, so 2 plus 2 plus 2 plus 2. Okay, so total become 8. And now then you will get a total cost 5 into 4, 20. So there are multiple possibility to get this. So what cost you can achieve the maximum here? Okay, so the solution is given. If you cut it like this as a 2 and 6, 2 plus 6 size. So for 2 you are getting 5, and for 6 you are getting 17. So total 22. Then you are getting 22 cost. If you cut the rod in this size and if you sell both, then you will get a total 22 cost for this. Then you can achieve the solution for this. So here also you can think about the same two-dimensional approach. One is for the length, what length is given, so that you can take as a number of rows. Okay, so length is given as a n, so you can take that as a that number of rows, how many rows you are getting. And for columns, okay. Column here also you have to take the n. Okay, so that means you have to make this matrix as a n by n. So that means possibility you have to take all the possible combination. So that means according to the size. So that means suppose you have the 8 here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 0 we will also take as a base case here, and same as a column. So 0, 1, 2, this one. Okay, so 0 here. 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Why we are taking this? Because we can achieve the size like 1, and then we can get the another size. Okay, so 1, if we are taking 1 plus 1, then what we are getting the cost, 1 plus 2, then what we are getting the cost. So here doesn't matter that you are achieving the full size or not by cutting the rod. Okay, suppose if you are getting maximum plus 3 plus 4, then you are getting the maximum by this. And maybe you are getting the 1 plus, then you can take this. So maybe the possibility is I think the possibility. So I think not possible. Okay. So multiple possibilities there. You have to check each combination here. Okay. So that what is the solution for if you're taking 1, 2, and then another possible size. Okay. So 2 plus 8 like this. 4 plus 4 here also. Okay. So in this way. So each combination you have to fill here. So by taking this 2 matrix size. After that, just fill this by 0, because if there is no size on the other side, you cannot get any profit for this. Okay, so 0, 0, just fill this. And same for here.
What is the y and x axis?
Both are actually n here. N means the length of the rod, because we can cut from any okay size. So we can cut from either 1, we can cut from 2, we can cut from 3. So because of that, we are checking the all possible combination. Okay, so all possible, if you're cutting 2, then what will the remaining size? So that means 6. That means okay. And here we also maintain the things, that means we can take the size of 2 and how many 2 into 4, that of size 2 we can take. Okay, hold on a second. Okay, so let's take one item here in size. Okay. So actually, the here one side is representing that how many piece we can cut. Okay, but what is the maximum possibility for that piece is 8. Okay, so that means suppose if you are taking the size that one piece, so what the maximum size we can cut of the piece is 8 total. Okay, if we are taking 2, then we can cut the size 2, maximum 4. So 2 into 4 become 8. So that because of that we are taking this one, but we have to take the size for equal in the both sides. Okay, because the maximum possibility, if we are taking this 1, that means we have to take as a 8 piece, one of the one size to achieve this. If we are taking that 8, we need only 1. We are not cutting. Okay, so we are not cutting, we are taking the length of 8, then 1 piece is only required. So in this case, by looking this way, we are just thinking here. So in this case, we will fill this. If we are not we don't have any size. Okay, if we don't have any input size n, then there's no output. Same things if we are not getting any number of piece. So same things, we don't have any output. We are not taking any number of piece. So because of that, we fill this as a base case. After that, we will fill by the same way like this. And then we will check if the length of the rod is 1, and we can take the 1 piece. Okay. So what will be the cost for that? So we will directly just read our, so cost list is already given. So that we will fill here. And also at the time of condition, so here now we will follow the same condition which we have discussed in the previous example. We will run a loop for each row and to by this location. Okay, so we will fill this part only and row wise row. And for each location, we will check if our length of I minus 1. Okay, so length of I minus 1. So this is I and this is j. So length of I minus 1 is just representing what are the length. This is the length. So that TP, if this is the TP, so length we have okay, so what are the possible lengths we can take? We can take one length, we can take two of these things. Okay. The length we are considering that is this one. This is less than the this one. Node size. This is the piece size. Okay. Okay, so this column is representing as a piece size. Okay, what piece size we can take? So 1 to 8 we can take. But this side we are taking what is the input length of the rod. Okay. So what is the length? Rod actually length is there. So suppose we have only one length. One end is given as a one length of the rod. Then what piece we can cut from this? Okay, so only we can cut one length, one capacity is there. Okay, so we can cut this. So we will fill this by like as a one. In this way, suppose if we have one length and we have the two capacity, so still we can only get the one length because our limitation is only one. So that we will fill by here. So what is the maximum? What is the length? One length is only there, so that capacity is there. Please, you cannot achieve. That's not that. Okay, here actually we need to calculate store the price, not the length. The one. One second. So let me just give we are taking length here. Minus one. If this is satisfied, then we can continue. Next price list. Price of that item. Okay, so yeah, this is very similar here. So length is this side is length actually, and this length, if this length is less than the capacity or less than or the equal to the capacity, then we can cut this. Okay, so we can cut this capacity, and we will just pick the price for that. Okay, we will pick the price for that capacity. What is the price is given for that capacity? So if you are picking that one is, so that means the one price we are taking. So here that price we will put here. Okay, then we will when we will check next. So now we got that. Or if we have the length one, so what is the price we can cut? So now when we are looking this second, so same things. If length is for this is less than to the j, so same things we can only cut one piece for that. So that size 2. So because we have only one length, so 2 minus 1, that means 2 minus 1. So that is the one possible. So the cost will remain same in this row because we have only this one length. Okay, so we cannot cut any more size after this one. But if we have two, suppose if we have the length of this rod is 2 now, then we can see, so we can cut either 1 plus 1. Okay, so we have the that cut is 1. What is the solution for cut is 1. So that we will check what is the solution for this one we are taking. So that we will pick. After that, what is the remaining capacity we have? So that we will also add directly. Okay, so for
So the
next
vertical
one.
is the line rod capacity.
Vertical line is representing a length, we can understand what the length, rod length is there. And
Total.
not vertical, so this row actually this row side actually representing the length of the rod, input length
Total
of the
length.
rod, total length. Okay, and this side we are just assuming that the piece size. This side we are just
Okay.
taking the piece size. And then we are just assuming that what is the piece size is given if our length is less than to the piece size. Okay, then we can cut that piece, and after cutting the piece, what are the remaining that we have? What are the remaining piece we have? So that we will directly take the solution for that. So that we will use this formula. So that max of that price I minus 1. Okay, so that I minus 1 is because of that the same region, because our list indexing is started from 0 indexing. So because of that, we are directly reading here. And then plus DP solution. Okay, what was the solution for that previous length? Okay, so that okay. So in the previous example, J. So J minus, and what length we have cut. So that length we will indicate by the I here. One, two, three, okay. That is indicating by the I. So I directly, and the another solution is so this is taking, we are directly here we are taking the solution from the same row. Why we are same row? Because we can take the same size again for the previous. Okay, in the previous example, if we have taken the current item, that means then we cannot take the same item again, because we have the only limitation of the, we have one item for each. So we are, if you are selecting the first that current item, we cannot select the same item again. But here, that if we are cutting the same size, we can cut the same size again. Okay, so if we are, suppose we have the length 2, so we can cut 1 and then again 1. Okay, so both same size. There is no restriction on that. If we are cutting the length 1 by 1 piece, so same things we can cut again. So because of that, we are looking the best solution on the the same row. In the same row, we are looking the solution of the remaining capacity. What is the remaining capacity we have? And otherwise, then we will just directly pick the DP solution for that same I minus 1 and the J capacity. Okay, without just including that size. So by this, in this way, we will fill the max value. Else part, we will directly fill this. Okay, DP I minus 1 and J. So in this way, your that matrix will be fulfilled, and the same last column in the matrix, you will get the answer at the end combination. You will get a maximum solution. Okay, here the condition only is required so that this I is less than equal to J. So what length you are currently picking, if that length is less than equal to the given capacity, so then you can pick that. Just try to solve this by the same approach. So that is logic is very similar. Only just try to make this table and just observe that are you getting the solution for the small part or not, and then just okay. Otherwise, now this is the last live coding solution, and then next week is free. Week 10 is there no content. So in the next, I think the next week we will discuss again on the live this dynamic program. Okay, maybe some more. So already, and that is there. Okay. Okay, just try to solve this. Otherwise, we will discuss this in the next. Okay. Also try to solve that coins problem. Okay, so that we can solve that coins problem using the DP approach. So that we will also discuss in the next session, okay, before the OPP exam. Okay, any query anyone, or shall we close?
Sir, can you show that using some in the table itself, the logic using some
So
example?
that,
Like instead of 8, like 4.
which part?
Also, this table, like the logic using some small
So that
length
yeah,
rod.
logic is very similar to the previous problem. Only the matrix part which is given here, the size is n by n, and here actually we will consider this side as a length. Okay, so if we are looking this, that means I. So what is value we are taking I? So that I kept this length should be less than to this that j value.
So J is the total length.
No, j is the piece size.
Okay, so J is that column.
J column, yeah, column.
Okay, sir.
Okay, just try to solve this, or you can just think other approach also if you found easy. But think about the same area. Okay, so just try to solve some small part, and then just get how you're getting the solution for small and how you can use the solution without calculating again in this way. Okay, same way.
Is there, can you share the code in the chat?
You shared? No, code actually I have not written.
Okay, sir. Okay.
Okay, code I have not written yet. Okay. Okay, then we can close the session. Thanks, everyone. We discuss in the next session if anything remaining. Okay.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Okay. Bye.